Hey there, everyone. Welcome to the solution video for Recitation 20, Saddle Node Bifurcation. If you don't recognize me, I'm Brendan. I'm the LSC instructor for the support course. Before I get into it, I just want to make sure everyone knows that our courses are still available. And this is the lecture schedule, and this is the office hours schedule for my tutors and I. If you want access to the LSC lectures, just send me an email at bjc297@cornell.edu. The office hours schedule should be already on the Math 1106 Canvas page, so you don't necessarily need access to my Canvas to access the office hours. So let's get started. So we're talking about saddle node bifurcation, specifically the Spruce Budworm outbreak. So we have these budworms. They're the prey, so to speak, and we have birds, which are the predators, and we want to model the population of the budworms. In some cases, they're in a nice equilibrium with relatively small numbers of budworms and however many birds. But sometimes we run into this situation where the budworms population explodes and it does horrible things to the environment. So what we're trying to figure out is why those explosions happen, how we can mathematically model them. So let's get started. Okay, so problem one, we're given the population model, the x prime equals equation. And it's this kind of messy thing. So we have x prime equals rx times 1 minus x over k minus x squared over 1 plus x squared. We're given that the first term represents the growth. This here is the growth. And this second term represents the predation by the birds. First question we're asked, what kind of growth are we looking at? So if we look at this term here, we see it's rx 1 minus x over k. That should look familiar. Specifically, we know this to be the logistic growth model. This is the logistic growth model. In other words, it's the population growth model with crowding. Okay. In part B, we're looking at the predation term. So we're looking at x squared over 1 plus x squared. We're given the graph below, and we need to describe in words what this thing actually looks like, what this means in terms of the context of the problem. So if we look here, as x increases, as the number of budworms increases, at the beginning we start to see an increase in the rate of change of this thing. People might know that as the second derivative, but as more budworms enter the system, the birds are eating the budworms quicker, right? They're eating more and more budworms. And throughout the entire graph, we see that this thing is increasing. The more worms there are, the more food that the birds have. But what's interesting to see is that as x gets quite large, we start to see that the graph flattens out. So what we can say is for small x, predation increases. And I'll write it over here. And I'll say fairly rapidly. And for large x, for large populations of worms, predation increases, but it increases slowly. Right. And this is going to be interesting to see how that specific aspect of the curve affects the budworm's ability to reproduce and increase its population. So we move on to question 2. And this is the more, I'll say, mathematical aspect of it. So we're given the original equation again, and we say if we factor out the x in the equation for x prime, we get x times this mess, r times 1 minus x over k minus x over 1 plus x squared. If we set x prime equal to 0, namely if we try to find the equilibria of the system, then we either have x equals 0, which should make sense because if there's no worms, then they're not going to increase in population. Or we get that r times 1 minus x over k minus x over 1 plus x squared equals 0. In other words, if we take this term and move it over to the other side, r times 1 minus x over k equals x over 1 plus x squared. What we're going to end up doing is we're actually going to graph both of these equations, both of these functions, this r times 1 minus x over k and this x over 1 plus x squared. We're going to graph them separately. And we're going to see where they intersect, because wherever they intersect, that's where our equilibrium points are going to be. So first, we're going to look at r times 1 minus x over k. It might look a bit complicated, but this x here is really the only variable on the left side. This r and this k, these are constants. So this should remind us of something like mx plus b. And just like it says in part A, this represents a line. So we're going to rewrite y equals r times 1 minus x over k in the slope-intercept form. Specifically, we're going to rewrite it as y equals mx plus b. That's the slope-intercept form. So what do we have here? If I take that equation we can distribute the r, and I'm going to rewrite this second term as such, and I'll just so that I can fit the exact mold that I'm looking for, I'm going to rearrange the terms. This is what we have. We have negative r over kx plus r. So from this, we can determine the y-intercept and the x-intercept. The y-intercept, right? This is where the line crosses the y-axis, and the y-axis is equivalent to saying that x equals 0. So this means that y equals negative r over k times 0 plus r, which is just r. So the y-intercept is y equals r. That's convenient for us. We need the x-intercept now, and that's equivalent to saying that y is equal to 0. And so we get 0 equals negative r over k x plus r. I can multiply, well, I'll bring the negative r over k x to the other side and multiply by k. What we end up with is rx equals k r. And as long as we can assume that r is not 0, which makes sense because if r was 0, then there wouldn't be any population growth. Then we have that x equals k. That's also very nice. All right, we have y equals r and x equals k as our intercepts for the line. So that'll actually help us graph this thing pretty nicely. So we'll move on. Now we have the graph of x over 1 plus x squared. That's the other side of that equation for the equilibria. So as we determined already, the y-intercept is r, and the x-intercept is k. So we need to draw the line in part B. We need to draw the line r equals 0.4 and k equals 20 and find the equilibrium points. Okay. So with that information, it's quite easy to draw the line. We know the y-intercept is at r, so if r is 0.4, we're going to put the y-intercept right there. And if k is 20, that's where the x-intercept is. So our line should look something like that. Let's make it a little thicker. That didn't help. Let's make it even more. That's better. Okay. So we have this line now. Like I said before, we're looking for where this line is equal to the given curve. And the line and the curve are going to be, well, the functions are going to be equal at the intersection points. So we seem to have 3 intersection points here. We've got this guy, and this guy over here. So we have 3 intersection points. We're looking for where the equilibrium points are located. So it's reasonable to, I guess, as to what the x values are, because we really don't have a set way to determine that from the graph. So we're just going to estimate. So what would that be? That would be these guys. So that might be 3. That's probably 16 or so. So we can make a guess. I'll say that x is maybe a half. 3, and I'll say 16. You might get slightly different numbers depending on how you visualize the graph. You know, the answer key might have slightly different numbers, but this is the general idea. So we want to draw a phase portrait indicating clearly the equilibrium points and their stability. So this is basically a fancy way of saying we want a number line. And so we are going to draw such a number line. I'm too lazy to get the shape, so what I'm going to do is use a nifty PowerPoint feature. Yes, it is what I meant. I wanted a line. Okay. Get it. So from this, we want to mark off our equilibrium points. I'm not going to draw it to scale because it doesn't matter. So in order to determine the stability, we need to determine if x prime is positive or negative in each of these intervals defined by the equilibrium points. So if you remember, our x prime was x, and then r minus, or sorry, not r minus, r times 1 over 1 minus x over k, and then minus x over 1 plus x squared. Okay, so this will be positive when this term is positive. We can assume that x is always positive because we're dealing with a population here. So we're looking for when this thing is positive. Specifically, we're looking for when the equation of the line is bigger than the equation of this red curve. That's when we're going to have positive x prime, and that's when we're going to have increase. The other case will result in x prime being negative, so we'll have a decrease. So if we look at the area of the curve from 0 to a half, this little blue line here is bigger, clearly, than the curve, right, in that interval. So that means the line's function is larger than that of the curve, and so x prime is positive. And so x prime is positive, which means that x is going to be moving towards 1/2 in that stage. From 1/2 to 3, the curve is actually larger than the line. So this x divided by 1 plus x squared is going to be bigger than r times 1 minus x over k. That means x prime is going to be negative, and we're going to be moving to the left. From 3 to 16, it's like the first case. The line is bigger than the curve, so we're going to be moving to the right. And then anything bigger than 16, the curve is bigger than the line, and so we're going to be moving to the left. Part D asks, how many stable equilibrium points are there in the phase portrait you just drew? At these equilibrium points, is the Spruce budworm population small, medium size, or large? Okay. We're looking for stable equilibrium points, and that's where the arrows are basically pointing inward towards that point. So it looks like we have 2. We've got 1/2, and we've got 16. 3 seems to be unstable. And so we have, for part D, we have 2 stable equilibrium points. X equals 1/2 roughly, and 16 roughly. Again, these numbers that I'm getting are estimations. They ask, is the population small, medium size, or large? It seems that 1/2 is going to be small in this context, and 16 is all the way out here. That's going to be large in this context. Medium size results in a unstable equilibrium point. Now that's interesting because what we were talking about at the beginning, we have relatively small cases of or relatively small numbers of budworm, but sometimes it reaches a point where the population explodes and we end up with a large number. So what happens if at any point in this particular equation, if our population ends up going over 3, maybe it's in thousands or something, if it ends up going over 3, then our system is actually going to trend towards 16 rather than 1/2, which is normally where it was stable. So that could explain, these explosions. All right. Okay, so now we're doing the rest of part 2. Basically, we're just redoing these steps for different lines. For r equals 0.15 and k equals 20, and then r equals 0.65 and k equals 20. So let's get those. 0.15, so that's about there, and k equals 20. And again, let's make this a bit bigger. And then we want another line at 0.65. So that'll be all the way up here. And we'll make that orange, and we'll make it thick again. Okay. So we have our 2 lines. So I'll do 0.15 and k equals 20 down here. Okay. So we are looking for part B was basically find where the equilibrium points are after drawing the line. So for 0.15, that's going to be very, very close to 0. And that seems to be the only one. So I'll say we have an equilibrium point at x equals, I mean, this could be 0.1, perhaps, very small number. Okay. If we draw our phase portrait, yikes, okay. If we draw our phase portrait, we have a equilibrium point at about 0.1. To the left of it, the line is larger, and so we're moving to the right, and to the left, or to the right of 0.1, the curve is bigger, and that's bigger the whole way through, and so we're moving to the left. We only have the one equilibrium point, so it seems we only have one stable equilibrium point. Right? And that's clearly a very small population. Okay. For the other case, for r equals 0.65, we also only have one equilibrium point, and that's all the way out here. Perhaps x equals 18. So at 18, yes, at 18, our orange line is larger than the curve pretty much the whole time, which is good. That means the x is going to the right, x is increasing. And then to the right of 18, the orange line is below the curve, which means x is decreasing. And so again, we have one stable equilibrium point. X equals 18. And this is a relatively large population. Okay. So suppose k equals 20. For approximately which values of r do we go from 1 to 2 stable equilibrium points and vice versa? How can we geometrically describe this situation? Okay, well, we know, it seems that for pretty much any value of r, given k equals 20, for any value of r, we're going to run into this curve at least once, right? What we're being asked is, when are we going to run into this thing more, right? More than once. So if I draw a new line starting at k equals 20, if we start, low, let's do this. Let's make it black, and let's make it big, like the others. So if I start low, we're in the case of intersecting the curve exactly once. If I start increasing and increasing r, what's going to happen is eventually, right about there, we hit the curve for a second time. This is interesting in that, and we can actually define the values of r. This is interesting in that it looks like the tangent line of the curve x over 1 plus x squared, and that's exactly what it is. At this moment in time, we have the line hitting the curve exactly twice. Once over with small x's, and then once somewhere in the middle. So that's probably, I don't know, the value of R is probably about, what is that, 0.22 maybe? But that's not the only tangent line that we have. If we keep going, and now we're hitting it 3 times, like in our case of 0.4. We keep going up, we're about here. Guess I'll just put it there. And now the black line is again a tangent line to the curve. In this case, now we're hitting the curve twice, once at this tangent point, and then once at a large number. And that's about R equals 0.55. So if we're talking about increasing values of R, 0.22 is the point where we go from 1 to 2, and 0.55 is the point where we go from 2 to 1. And I say X, I shouldn't have said X. I should have said R. And again, how can we geometrically describe this situation? These are the tangent lines. These are tangent lines to the curve. Okay. G is basically the same question, but for k equals 10, so we're going to draw a few more lines. Try not to bog down this image with too many lines. Let's see if I can choose a good color. Green is a good color. Okay, so we're at k equals 10. Increasing. Our tangent line, the first tangent line occurs around here, maybe a little higher, right about there. So that's slightly bigger than 0.4. I'll call that 0.41. And that's where we go from 1 to 2. And then increasing. Right about here at 0.58. And that's when we go from 2 to 1. Again, if we're considering an increase in R. Okay. So that should answer all the questions. And so we can move on to the last question, which is question 3, which is also on my last slide here. So now we're just summarizing. We're basically just summarizing what we learned. For k equals 20, describing words, what happens to the equilibrium points as R grows. Okay, so we can look again back here. As R increases, for R less than 0.22, I'll put it here. For R less than 0.22, we have one stable and small equilibrium point. For R between, what was the other value, 0.55? So R between 0.22 and 0.55, we have 3 equilibrium points. 2 of them are stable and 1 of them is unstable. And then for R greater than 0.55, we go back to 1 stable. And in this case, we have the black line here. The equilibrium point is going to be large. For k equals 10, it's actually quite similar, but the real difference here is that, for 20 it was 0.22 and 0.55. For 10 it's 0.41 and 0.58. That just means to transition from the different types of equilibrium points for different values of R, the values of R are larger. And so the birth rate of the budworms needs to be larger. So I can say for R less than 0.41, we have 1 stable equilibrium point, and again, the stable point is small. For R between 41 and 58, again, we had 2 stable and 1 unstable. And for R greater than 0.58, 1 stable, large equilibrium point. 2 differences, and I'll put the differences over here. So 2 differences. One, as I said before, these cutoffs for when the stability and the number of equilibrium points change is larger. So cutoffs for change in equilibrium points are larger. For R. The second one, which I haven't mentioned yet, K represents, if you go back to the logistic equation, which we talked about at the beginning, K represents the population cap, the carrying capacity of the system, at least without any predators. And so if, when we talk about large, these large equilibrium points, these are relative to K. So large just means close to K. So in the case of K equals 20, that large is more like 18 or 19, while in the case of K equals 10, the large might be 9 or 9.5. So large equilibrium point is relative to K. So K equals 20 has larger equilibrium points than K equals 10. Okay. So our final question, final part here. How many stable equilibrium points are there, or point is there, when K equals 3? So let's look at the different kinds of lines that we can have when k equals 3. So I'll just put this here, I'll make it bigger. So, if we have a small r, then we have one equilibrium point, a very small value for x. As r increases, we still have one equilibrium point, and it turns out that never really changes. As high as for r as we want to go, we're never going to run into a case, for this equation at least, where we have more than one equilibrium point. Equivalently, there's no tangent line that passes through the k equals 3 there for the curve. And so no matter what r is, for any r, there's exactly one equilibrium point. For any r. If we look at the phase portrait, and this is for any r in the whole world, we don't know what x is. I'm just going to call it x0. We can determine that the line is above the curve to the left of that value, this value in particular. The line is above the curve to the left of that value, and the curve is above the line to the right. So we're increasing and we're decreasing. So the equilibrium point is stable. That's for any r in the whole world. So if k is sufficiently small, then there's only one stable equilibrium point, no matter what r is, which means that if the carrying capacity of the system without predation is sufficiently small, then the budworm population will never explode, which makes sense, because if the carrying capacity is small, if the system capacity is small, we can't really see an explosion in population because it's still capped by the carrying capacity of the system. Okay, that should be everything. Thanks for watching this video, and good luck.